Cool.
All right, I'm recording. I don't know what my internet's going to be like tonight because my sister's also on a Zoom call. So can someone else also record, please?
You're not lagging today though, so it's good.
That's because she's not on the call yet.
Oh.
Yeah. David's going to be starting off with HKS stuff.
Do you want to do Kahoot
we
first?
do the Kahoot first? Yeah.
Or David, do you want to just go first because you might want to, I don't know if you're heading off early.
Yeah,
guys, follow Coffee Stat, but like David is like doing like a crazy like 5 a.m. challenge. Like I don't understand. Like
joining the club.
Yeah, man.
I literally don't understand.
Oh my god, is that why you were the gym up at like 5:49? Oh.
Let me get. Wait, Peter, do you want to pull the slides up?
Oh yeah, I can share
if you
screen.
can.
Yep.
Sorry, my iPad's on. Thanks. Yeah, so got to be in bed soon.
Yeah, it's going to be past David's bedtime.
Oh,
No
so
joke.
sad.
You guys are
Like,
crazy. Crazy.
Gotta get that work for that. All right, cool. Let's get down to business.
Okay.
I can't do this song. All right.
Yeah.
It's still.
Yeah, I know.
Oh, there we go.
There's just a lot of slides.
I'll make a man out of you. Dun, 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 dun.
Okay, buddy. There you go.
All right, primary healthcare in practice. All right, let's do this. Next.
All right.
Cool. So essentially, what is primary healthcare, right? Like if you think of primary healthcare, we think of like your GP, we think of your nurse practitioner in the community. It's very community-based, but actually primary healthcare is a little bit more complicated than that. And especially if we think of primary healthcare as something that's really important in maintaining the overall public health of our community. So essentially, there's a few factors that my theory will really emphasize. So firstly, evidence-based approach, essentially that what you do needs to have evidence behind it. There needs to be facts to support our clinical judgment. So it can't just be like, oh, I'm going to do this, right? Like it needs to be systematic. And we have these databases that have clinical guidelines called Cochrane Systematic Reviews. You'll see a lot of that in year 2 and like BMJ guidelines. So definitely look into that if you're interested. So there's also like intersectorial, essentially, since if you think of primary healthcare as being a part of the community, then you need to integrate like every different parts, right? Like you need to understand a bit about everything. So this kind of different cultures and people from different walks of life, you need to incorporate that people skills and that knowledge in order to be a very good primary healthcare physician. And that is what primary healthcare is. And of course, leading on from that idea, cultural acceptability, right? Like what is cultural acceptability? So if we think about Melbourne, right, even the people here tonight in our Zoom call, it's very multicultural. There's people from all types of ethnic origins, especially in Australia, there's like those of Aussie background. And if you're in another country, there's a lot of different locals. So essentially, it's just about being inclusive and understand how cultural practices may change your interactions with patients or with even other healthcare workers. This is just kind of a good rule of thumb in the way that you carry yourself in different cultural settings. Cool, next, thanks. And this is just like a few more. So you need to have technology, right? Like medicine only evolves as a result of technology. If you think about it, let's say one of your patients needs an MRI or a PET scan for a diagnosis of cancer. Well, how will this affect your plan of treatment? Possibly without it, you might not be able to fully make the diagnosis and give the specific type of chemotherapy you like. But so the answer is, by having accessibility of technology, primary healthcare can only evolve and help those on a larger scale. And this will also need to be factored into kind of a geographical accessibility. So like, let's say you live rurally, but you're not able to access the healthcare and technology within the city. So this is like the geographical kind of accessibility. There's also scarcity in economics. So it could just be distribution of resources that's kind of a problem. This is less on a less on an individual level, but more so on a governmental kind of scale about how they're going about giving this access of technology and ethic reviews. Moving on, so wait, just go back one. Sorry. Yeah. Oh. Yeah. So yeah. So sorry. Yeah. So participatory approach, essentially, that everyone just kind of needs to get involved. Affordability, I already talked about that. Like, if your MRI is like so expensive, like you can't afford it, then of course, like primary healthcare isn't going to be successful for a wide range of people. And the first point of contact essentially means that, well, it's your GP, right? Like, if you feel like a little bit sick, if you've got a headache, this is the first kind of person you will see, and they really go about screening different diseases and making sure that the specialists as well as the hospitals are getting overwhelmed and people are getting the immediate care they need within the community setting and not in an inpatient setting. Cool. So this is one of the biggest examples that you guys have to remember for HKS. It's called selective primary healthcare. So it's not like primary healthcare for everyone. We're specifically having a program that is affordable in order to have the biggest impact. So it's kind of a cost economics kind of analysis. Well, one of the most famous examples that you guys do need to remember this acronym is GOBI FFF, GOBI FFF. I think of, like, you know, the GOBI fish, like the puffer kind of fish thingy. I'm not going to do his face. So GOBI FFF, right? So G, growth monitoring, oral rehydration therapy. So oral rehydration therapy is like used a lot in like dehydration, of course, and like cholera or any of these like diarrheal diseases, breastfeeding, immunizations, female education, food supplements, and family planning. As you can see, all of this is not focused on like this wide population. It's rather focused on these specific demographics. So in this case, we're focused on children and women. And it does have wide-ranging effects, so that it actually saves approximately 7 million children a year. And by saving them, you actually save the economy as well. And there's basically four relatively cheap methods. So that's just in your growth monitor, your GOBI part of the GOBI FFF. Really has evidence-based efficacy. Think back to what we talked about the first point about what makes primary healthcare. It is that evidence-based practice. Immunizations, especially in developing countries, one of the examples My3 uses is like malaria. So that really does make an impact in the overall community disease burden. This is just a bit more philosophical. It's more so from a literary perspective. So essentially, Michael Foucault, I can't pronounce his name, my bad, but essentially he coined the term medical gaze. So it's to denote dehumanizing medical separation of the patient's body from the patient's person. Sounds really complicated and convoluted, but basically it's saying that I'm only looking at the disease and not the human. Well, obviously that's wrong, right? Like, in the sense that the patient shouldn't be defined by the illness. They're far more than that. They're rather an individual with a story, and rather they just have that disease. So in colonialism, this view often comes through because they don't want to, they don't want to see the original inhabitants of the land as equal as people as themselves. So they only see it as a disease. And you can see how this obviously would impact the way that we're treating people even to this day. Like, we need to constantly remember that colonialism and the post-colonial era will still have far-ranging impacts even to nowadays. Basically, strong medical paternalism as a result of colonialism. Yeah. Development of neocolonialism. This is essentially capitalism on steroids without any rules. I think that's probably like the best way to put it. Essentially, it's we think about it as that's neoliberalism. Neocolonialism is just the part after neocolonialism when everyone is starting to develop. There's not too much on this side, to be honest. My3 doesn't cover it that much. So this is what I was talking about just then. So essentially, neoliberalism is capitalism on steroids. It's without control, it's without governmental input, so people are allowed to gain wealth without any rules, without any controls of the state. Essentially, this means that people can get really greedy and unrestrained ambition. So neoliberalism just allows us free markets to maximize these profits and a lot of the wealth gap becomes even greater, leading to also, as a result, a healthcare differential between the wealthy and the poor. So capitalism, in the definition of HKS, is something that is good. It is allowing people to gain wealth within the controls of a state. Whereas neoliberalism is kind of like cancer. It spreads far too much and has heavy impacts on people who might not be able to gain this wealth. So just remind of the 4 S's. We talked about this on the first HKS, as well as your first Health and Knowledge in Society lecture. So staff, space, systems, and stuff. So you just need to know all of these and to be running, you need all 4 of these to run efficiently in order to have effective primary healthcare. Think about it, right? Like a GP, you need to like not just have the GPs, the doctors, but you also need to have like the admin staff. You also need to have the cleaners. Space-wise, in a hospital, you need to have like theaters, operating theaters. You need to have these like wards, systems-wise, like healthcare systems. So that's like Medicare. Without that, it's going to be really difficult for patients to get the rebates and stuff. Like if you don't have the equipment, how you going to treat? Yeah, next, thanks. So essentially, just to wrap it all up and some things to keep in mind, just understand that primary healthcare requires basic systems in place and it's a first line of treatment. And it is the best line of treatment if we can catch diseases early on. In this day, essentially neoliberalism, we need to be focused that in our own clinical practice, we can't just be focused on the disease. The patient isn't defined by the disease, rather the disease is just something that they have. My theory goes into quite a few examples from malaria to AIDS in this lecture, but just the main thing is familiarize yourself with these scenarios and stories. Think about it like how you might react and what the best way to go about all of these things are and what went wrong, what could be done better. And just think about how, if you were going to write a short answer response, what your opinion would be on it and what some suggestions could be in making it better. And these suggestions could really come from the 4 S's. So that by having that framework in mind, it really helps you answer these short answer questions. Yeah, okay. I think that's me done. So thanks, guys.
Yeah, sweet. Does anyone have any questions about HKS?
How do you use the staff, space, systems, and stuff to answer short answer questions?
Yeah, so are you saying like how do we answer these short answer questions with the 4 S's? Is that what you're saying?
Yes.
Yeah, so let's say, for example, the prompt is saying that you're currently a rural GP in a community that's mostly at-sea heavy, and you just arrived and realized that the patients aren't receiving the care that they deserve. A lot of people aren't getting like the checkups they need, and that there's a heavy community disease burden. So they would usually write out like a little mini paragraph that you kind of have to answer, right? Well, how do you go about answering it? So let's say we have using 4 S's. So firstly, you could be like, firstly, the staff, like, is it just you, the GP, or do we have anyone else in the community that can help out? Like this includes like, do we have healthcare workers, other healthcare workers, admin staff? Do we even have like people able to help us drive patients around because they might not be as mobile? And if we think of spaces, so like you need a GP clinic and you need even screening clinics. And we even need hospitals. Like if you don't have the hospital in town, like where is the nearest one? So these are just kind of things you think about. Systems, like for example, why are these people getting the care they need? Is it because that they don't know how to use Medicare? Is it because they aren't getting the rebate that they need? Is it because there is a language barrier and a cultural barrier that the systems are in place that's preventing them from getting the care they need? And in terms of stuff like, do you even have basic like testing kits for like, I don't know, even for like the basic blood tests even, right? Do you have the materials that you need? And if you don't, like what are some ways you can go about improving that? So I think Maithri will talk about that in the Indigenous Health lecture more specifically. So I won't cover that.
What was the systems part again?
Sorry, what was that, Rachel?
The systems part.
Yeah, so for example, just like what I was saying before, like the systems, like you need to ask yourself, like, why is this system possibly not conducive to people going and getting the primary healthcare? Is it because that there is a systemic injustice, like the English might be written really complicated and that they can't fully understand it? Or is it like a cultural barrier between the doctor before and the Indigenous patients? Is it because that the cultural gap is like, I was like, oh no, they practice Western medicine and whatever I'm saying, like the doctor just shuts me down. So you see how there's a system problem here? And like later on, like, do they not go to the doctor? Because it's expensive. Why is it expensive? You ask yourself, well, like don't they have Medicare? So if the system isn't in place to actually help them get that rebate or like the money back from the government for their healthcare, then that system is going to impact them from seeking more health assistance. Does that kind of make sense? The system?
Yeah, thank you.
No worries, all good. Any other questions? Yes, no. Okay. Well, if you do, just send it through the Google Sheet and I'll make sure to answer. Or just send me a private message on Facebook. Always happy.
Zoe, do you want to take it from, oh wait, no. Do we want to do Kahoot? Yeah. Yeah? Right.
Yeah, I think we promised we'd do that at the beginning, so.
Yeah, let's do Kahoot.
All right, sweet. Is it on your account, Patrick? Okay.
Yeah, I can open it up.
Yeah, could you open it up? I think, yeah.
Week 7 Kahoot's pretty spicy. I put some really hard questions in.
But week 7 is next week. We'll be doing that Kahoot
good.
next week.
All right, you guys better tune in. The questions are kind of not that hard, but a little bit harder than me. Also, I got a question today from someone about your anatomy quizzes. Someone messaged me and said that essentially you guys got a quiz that asked you, a patient presents with weakness in the left lower limb, but no sensory deficit. It could be caused by growth causing compression on what structure at the approximate spinal level. So this question got me so confused. I was like,
did we ever
learn this? Like, this is so hard. And then I'm like, wait, no, this is like your DCML, your spinal filaments. Like, you need to think about the contralateral like shifts in vertebral level, like at which point. But like, I don't think we went into this amount of detail, like ever. We just knew there was spinal tracts. Like, that was it.
Isn't that like semester 2?
Yeah, that's more relevant for semester 2 stuff.
Yeah.
So don't stress too much about it if you find anatomy too hard right now. Mainly focus on your epithelium, connective tissue, like your basic stuff. Like that's actually like, let that be your basis.
Yeah, Jay. Do you want me to explain things or do you want to explain the questions? Or does, I don't know who made it.
I'm okay either.
Okay.
Just take turns.
Okay, yeah. Easy. All right. Let's get 25. A couple more.
Oh my god.
Not wrong.
David, don't expose yourself. 26. There could be one more, but I think we could probably get started.
Yeah, they can join after.
Yeah.
Creative equals 3. Oh my god. It's the anatomy name.
Let's go.
This is covering week 5 and 6 content, by the way, guys.
Wait, is this the correct code?
No.
Wait, this is week 7
Oh,
content.
Yeah, this is week 7 content. Hold on. My bad. Sorry, guys.
You see what I mean by
Sorry.
spicy content?
Wait,
No, to be fair, they haven't learned it, that's why. So
Don't worry, guys. We'll be going through it in a sec.
How are
Sorry, guys, hold on.
How are all the lectures yesterday and today so far? Like, were they decent lectures or not great?
What did you guys do today?
And yesterday. Nice.
Came out a day late. Not
ain't
surprised.
that a mood? Just don't watch it. No, you should.
If they come out a day late, you can go and watch like our lectures. Like you can go to General Resources and there's like past
They are the ones.
2019.
They are the ones from last year.
Yeah, if you're like that keen. So
Do you guys know the dates of them? If not, I reckon if you don't have our schedule, we'll try and dig up our schedule and we'll just give it to you, and then you can just like do reverse engineering to find the date rather than click into every single one.
The contents in the muscle lectures was different. Okay.
Oh. Okay.
What was different about it?
I'll just unmute myself. Like different as in it had more stuff. Like I went through the last year's lecture and then I was like, oh, I'll just like skim over the 2021, and then there was more stuff and I was like, oh.
Wait, was this Michael?
What's going on?
Pardon?
Is it more stuff or is it in more detail? Is the real question.
Some stuff's a little bit more detailed, but like not really significant. But like I'll find something and I'll like show you.
Yeah, because with Michael, he mentioned that he'll put more like stuff in because we complained to him, and he was like, okay, I'll try and make it more clear next year. So it seems very weird that he's added more stuff.
Yeah, we have a different lecturer doing the
okay, yeah, that makes sense.
So yeah.
That's a big rip.
Yeah.
RJ, how do you feel?
RJ, all of this appreciation. This is what you deserve.
Is this everyone? 27?
I think that's how many we got last time.
Yeah, that's everyone.
Let's go.
If you're like me and you hate the Kahoot music, you can mute the shared sound on the view options.
Okay, it's not too bad. So basically for parasympathetic, you need to know that it causes all these 3 other things. It's something that you need to, you just need to get used to. So parasympathetic is more of rest and digest. So it'll cause contraction of your GIT. So this is not the option. It's also, because we say it's rest and digest compared to your sympathetic, which is your fight or flight mode. So your fight or flight mode, your heart rate will go up. So bradycardia is the opposite. It actually goes down. So parasympathetic does that as well. and bronchoconstriction. Again, like sympathetic, it causes bronchodilation because you want to be able to take in deeper breaths so that you can like run away faster, you know, the whole fight or flight kind of thing. But parasympathetic is the opposite. So that's why the only option is dilation. All right. Oh, nice. Okay, that's great. Like majority of you all know this. So Monash loves to ask you this question about telomeres. You just need to know psychological stress causes telomere shortening. It's something they ask all the time. Okay, not bad, not bad. So for this, it's some statistics that you need to remember, and they love to test all kinds of statistics. So you just have to revise your HEP for this. You just have to remember this percentages. There's quite a few in our course. You just have to keep on practicing, you'll get it. Okay, not bad. So meditation is actually a formal type of mindful practice. So there's informal and formal. So formal is when you actually actively try to do a practice to improve your mindfulness. And informal is like deep breaths and other things. Okay, so for ATSI status, you need to know that there are three main things that you need to have. So you need to identify as ATSI, and you need to have a proof of lineage, as well as a community. You need the community to accept you, but you don't need a biological background. So you don't necessarily have to be born within the community to attain ATSI. Okay, so this is actually false because it's a type of negative punishment. Yeah. Peter, do you want to explain this?
Yep.
Like 3, 4.
Yeah. Okay. So consider this scenario in two sections. So there's one section is taking away money, and the other section is not doing homework. And if we think about not doing homework, in this scenario, we consider not doing homework and it's like an undesirable action. So therefore, we want to discourage this action. And therefore, if we want to discourage this action, we want to punish them. So right from the get-go, we know that this statement, that it's negative reinforcement, is false. Taking away money, so in this case, taking away money is removing a desirable stimulus, and therefore it is negative. So the negative part of negative reinforcement is correct, but reinforcement is incorrect. It should be punishment. And therefore, this statement is false because it should be negative punishment. Good night, David.
Bye.
Okay, nice. So for this question, you just have to remember the 3 Ps. So potassium phosphate protein are always going to be higher inside your cell. And everything else is higher outside your cell. Okay, not bad. So for maintaining RMP, it's maintaining it at -70. So it's actually your leaky channels, your potassium channels, which are actually open throughout, which help to bring down the value to -70. Your voltage gated are used for depolarization as well as for repolarization. Okay. So for relative refractory period, you have to remember that it's during your hyperpolarization phase when it drops below the -70 mark. So that's when you need an extra stimulus to even achieve AP. That's why it's called relative, not absolute. Okay, nice. So this one, you just have to remember the order is actually the opposite. So 2 potassium are pumped in and 3 sodium are pumped out. And this is something that's very important that you should remember.
Yeah, just to jump in here. So there's a useful acronym I saw, and it's basically 3, 2, 1, Nokia. So you kind of match up the numbers to a certain level. So it's 3 sodium out, and then it's 2 potassium in, and it requires 1 ATP. So that's a good way to remember that one.
Okay, nice. Okay, this is pretty good. Just to look at the wrong answers, AP is actually all or nothing. It's not graded. So once you hit the threshold, you'll generate an AP, and it can travel long distances. The main thing that AP is cannot do is that it cannot be bidirectional. It's always one way. Oh, okay. Okay, this is very important. So your K, when you repolarize, you actually can repolarize through your K voltage channels or through your leaky channels. So if you have your K voltage channels which are open, your membrane potential will then hyperpolarize and then go back to normal. But if that doesn't work in a person who doesn't have K voltage channels, your membrane potential can actually still go back to its original. It'll just take a longer time, but it won't hyperpolarize. That's the main difference that you need to know. And this is because of the leaky potassium channels. Okay, so you need to know your examples of inhibitory and excitatory neurotransmitters. So acetylcholine is an excitatory neurotransmitter, and it's very important that you know that. It's always used for neuromuscular junctions to allow for constriction of the muscles. And GABA is your main inhibitory neurotransmitter that you need to know. Noradrenaline is also another excitatory, and glutamate is used in your CNS, and it's also excitatory. Guys, can someone overtake the top? Please.
Good job to whoever's at the top. You don't have to reveal yourself, but you can if you want to. I don't know. DRG stands for dorsal root ganglion. Yep.
Yeah.
Nice. Good job.
So, yeah, majority of you got this right. So, your cell bodies of your sensory neurons, they're going to be found in your dorsal root ganglion. Your ventral horn actually has your cell bodies of your motor neurons, and dorsal horn has the axons for the sensory neurons and like the terminal end. But the cell bodies are found in your DRG. Okay, nice. So quite a few got this right. You need to know your pathways for your DCML as well as your spinal thalamic pathway. Decussation is when it switches sides, and for the DCML, it switches sides at your medulla oblongata. Then for spinal thalamic, it's at the same level of entry.
Class.
Okay, that's good. So, yeah, your innate immunity response will always be the same every time you have an exposure to a virus or a pathogen. And yeah, and it'll be broad range and it's rapid as well. Okay, yeah.
This is just kind of like a fact you kind of just need to know. Like, yeah. It's in the slides, but yeah, C3A and C5A are the ones that enhance inflammation by attracting immune cells. Your C3B and your C5B, they're the ones that recognize PAMPs and actually like just like they coat the pathogen and then like attract them for like phagocytosis. And then basically C6 to C9, they're the ones that cause lysis of microbes by membrane attack complexes. So they're the ones that go around and like poke holes. But yeah.
Okay.
Whoever's playing whoever's that person is just too good.
Yeah, so this is the rule of 8 that you need to remember. So class 2 will always go with CD4 plus, and class 1 will go with CD8 plus. Okay. Yeah, so you need to know the roles of your different antibodies. So IgM is more prominent at the early stages of infection. IgA is for mucosal parts of your body. IgE is for interactions with helminths and worms, and autoimmune diseases. And then IgG is more prominent in later stages of infection.
Yeah, IgG is the one that you'll see, like if you get a serology test, it'll show like your past history of getting a certain infection.
Okay, last question. Okay, so you need to know your roles of your different Th1 cells. Th cells. Th1 is used for viruses. And that's the main one you need to know. I can't remember. Peter, do you remember what's Th17 and 2?
Th17 comes up in respiratory things, and I think Th17 comes up in respiratory, and it produces interleukin of some sort that strengthens the strengthens the epithelium or something.
Yeah, but basically you just need to know Th1 is for viruses.
Yeah, TH1 and TH2 are the main important responses to know for year 1. And even for year 2, TH17 isn't too commonly used. Well, it doesn't commonly come up, at least. TH1 and TH2 are the main helper T cell responses that you need to know.
Yeah, and CD8 is its own cell. CD4 doesn't become a CD8. All right. Okay, let's see the podium.
Let's see the podium, Ajay. Yeah.
Hey!
Oh, wow. Okay, let's start sharing.
Well, 20 out of 20. Good job to whoever got 20 out of 20 and to everyone else as well. Yeah, you can find RJ on Facebook. What? Okay, sweet. Zoe, do you want to take it?
Yeah, okay. Yeah. I'm gonna go through my part as well. I'm gonna go through vascular, lymphatics, and then muscle because I want to go to sleep as well. I'm so tired. Okay. So, wait, can you see everything? All good? Okay, I can't see. I'm just gonna keep going. Okay, so vascular and vasculature and lymphatics. Medium yield. You'll go through this a lot more in semester 2, but this is really nice to just form a like base level of knowledge that you can build upon, and also helps once you're actually in like anatomy lab and you're dissecting and you want to be able to tell the difference between an artery and a vein. These characteristics actually, like you can actually see the difference in real life in a cadaver. Anyway, so vasculature, so this is broadly talking about arteries and veins. They have multiple functions, obviously, so you can have oxygen exchange at the capillaries in your lungs, temperature regulation, pressure regulation, yes, rigidity to the penis, fluid regulation, filtration, absorption, blah, 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 blah. The main one you're really concerned about at the moment is kind of like, actually, you're not actually concerned about any of these yet. So, you're going to need to know the vessel anatomy. So, for both arteries and veins, you have 3 main layers. There are layers in between, but we don't really talk about them in first year or second year, really. The 3 layers are tunica intima, which is the inner layer, and that's just talking about endothelium, which is just like epithelium, but epithelium for blood vessels. And then you've got the tunica media, which is muscular, and that layer is important because it can actually, since it's got a lot of muscle in it, it can actually contract, and it can, if it's contracted, less blood can go through, and if it's dilated, more blood can get through. So it can alter the rate of blood flow it can alter the rate of blood flow. The 3rd layer, which is on the outside, is the tunica externa, and another name for it is the tunica adventitia. And that's just an elastic layer which helps maintain the vessel integrity. Important thing to note is that before I came into med, I thought that arteries were the things that carried oxygenated blood and veins were the ones that carried deoxygenated blood. That is not correct in all cases, and that's kind of like the main thing you really need to take away from this whole my part of the presentation. So how do we actually define arteries and veins? So arteries are tubes carrying blood away from the heart. So it's not they carry oxygenated blood, but they carry blood away from the heart. So it goes towards the capillary bed, and it has a like progression of small branches. So you'll have arteries, arterioles, and blah, 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 blah. There's stuff in between, but whatever. And it has more elastin than veins. They also have thicker walls relative to the lumen size, and they do not have valves. Keep that in mind because that shows up as a multiple choice question in the cardiovascular quiz in semester 2. I think about a competent exam as well, who knows? Yeah, arterial blood is mostly oxygenated, but not always. So the two main exceptions are the pulmonary arteries and the umbilical arteries in like pregnancy and babies and all that kind of stuff. There are 2 main types of arteries. actually they're not really types, but they're two main structures, I guess, of arteries that you kind of want to know. So those are elastic and muscular. So the elastic arteries refer to ones that are like really close to the heart. So as the heart pumps, it's actually pumping out the blood with like quite a lot of pressure. So the arteries that are nice and close to the heart and receiving the blood first, you kind of want them to be pretty elastic and be able to distend quite easily, so they don't like dissect or whatever. And so they have lots of elastin and like lots of elastic tissue in the media. That's the main key point. And the other type is muscular. So those have a lot more like smooth muscle in the tunica media, and yeah, and that's for like blood distribution and stuff like that. And on the other side, you have veins, so they carry blood back to the heart in all cases. Same thing. The unique thing about veins is that a lot of them have valves, and venous blood is mostly deoxygenated, similar to the arterial thing. But then the two main exceptions are pulmonary veins and umbilical veins. And you also want to know about the structure of the veins. So you have the lumen filled with blood, obviously, and you've got the same three layers for the vein wall. So the intima on the inside, media, then the adventitia. Okay, lymphatics. This was covered quite poorly from what I remember. You really don't need to know much about lymphatics in semester 1 at least. So you need to know that it has two roles. It has a physical role and an immunological role. In first semester, you just need to know the fact that it has an immunological role. So it's kind of like has like a role in the recognition of foreign antigens and like antigen specific cells. Just to memorize it, there's not too much to it. And then you've got some general principles for the flow of lymphatics. Not too important. Okay, lymph nodes. So we've got the lymph flowing through the body. The little nodes are kind of like where you kind of have, like it's like a little bean-like structure, and it's kind of like a sieve almost. So it's where like you remove the cell debris and stuff like that, filter foreign particles, recognize foreign proteins. So basically just have like a lot of immune function things in the lymph nodes. Another thing you might get tested on, multiple choice question, is what is a sentinel node, and that is just the site of the first spread of the tumor. So if you have like a tumor in your breast and that spreads to like a lymph node in like your armpit area, that first lymph node it spreads to will be your sentinel node. And then other things, brief little dot point is anatomy meets like physiology / like function or whatever. Lazarus always says that. The main point I'm trying to make is that near the portals of entry, so where the body meets the external world, you're going to need more immunological functions. So you'll have more lymph nodes near your skin, respiratory tract, GIT, and urogenital tract. Yeah, pretty self-explanatory. Comparing vessels. This was a active learning. This is quite literally just a screenshot of a 2-hour active learning. So I'm not going to go through it, but I'm not sure if you're going to have the same one this year, but these are the answers that you're looking for when you get to it. Okay, I'm going to skip pharmacology for now because I want to go to sleep and then just finish off my section. So I'm also going to talk about muscle. I don't know if you've done this. This thing, but all the muscle stuff is covered again in like greater depth in semester 2. We didn't really get tested on it in semester 1. So if you don't get it now, don't really worry about it. They'll just talk about it until you're sick of it in semester 2. But basically, you have a whole bunch of definitions. It's not that hard. The hard part about this is that basically you've gotten all your cell stuff, and then you've given like all your cell stuff new names. Yeah, because instead of being in the regular cell, now it's in the muscle cell. So now it has all new names. So you can see like sarcoplasm is the cytoplasm of a muscle cell. Cell membrane of a muscle cell has its own special name, sarcolemma. But the main one you kind of want to understand, at least at the moment, is what a sarcomere is, which is the smallest repetitive contractile unit. Okay, we'll get into that. And this is just a little diagram we can look through later that kind of summarizes all the different definitions. Okay, so do you guys remember if we did this, actually did the whole action sliding filament theory in semester 1?
Yep.
Oh, okay. So in skeletal muscle, you kind of want, whenever you have like, you know, skeletal muscle contracting, you kind of have like the muscle fibers like this, and you have them like moving together. So you've got all these little different like myofibril things, and whenever you contract your muscle, they move closer together, and when you relax, they move further away from each other. And basically, in each of those like myofibril things, you have a bunch of like lines and bands. So yes, you do need to memorize this. It will get tested. So you've got your A bands. Oh, wait, have you guys done actin and myosin? I can't remember what we did and we didn't do.
Yep, they would have talked a bit about it. Oh, well, like the ideas of actin and myosin have been introduced before, but not exactly what they are.
I don't know if I have a good diagram. Okay, so basic basic myofibril, you have like actin on the outside, and you have like thick myosin on the inside. And basically, you have a whole bunch of different zones / bands, which are important when you're contracting muscle. So a few of the ones you need to know are the Z lines, which are like where each like muscle cell kind of like ends. You have the M line, which is in the middle, and then you've got the thick filament, which is talking about the part with the myosin, and the thin filament, which is like a lot thinner, which is on the outside, which is the actin. And all the definitions are right there. I think for this sliding filament theory, if you actually want to understand it, just go watch some YouTube videos on it. Like I tried to understand it through a textbook for like 2 hours, didn't work. I watched one video, I understood it in like 2 minutes. So I highly recommend doing that. But the basic idea is that you have a bunch of actin and a bunch of like, you have these like actin things on the outside, the thin ones, and then you have the thick myosins on the inside. And whenever you contract the muscle, what happens is you're basically just moving the thin parts like towards the thick parts in the middle. So it's kind of just like moving together like that. So contraction, relaxation. And that's the basic idea of this whole thing.
I think you guys will go into more. Actually, no, sorry.
Yeah, there is in semester 2. There's a whole 2-hour active learning dedicated to this entire thing. Would you go over which section shorten when the muscle moves? Okay, wait, is this a multiple choice question? Okay, yeah, I don't have my pen. Anyway, so what you have is you have your Z lines. So these are your Z lines, which are the ends. I'm doing this with my finger. So these are your Z lines. And when the muscle contracts, your thin filaments move over your thick filaments. So your thin filaments move towards each other over your thick filaments. And then your thick filament kind of stays in the middle like there. So logically speaking, if these thin parts are moving closer together, your Z lines are moving in as well. So that's why during concentric contraction, which is when your muscle is actually shortening, your Z lines are shortening because your like acting, the thin filaments are moving towards each other.
But it's important to note that like none of the strands like actually physically get shorter. The gap between multiple strands simply move closer together. So it gives the appearance that they're becoming shorter, but the individual strands themselves don't become shorter.
Yeah. What else is there?
Does that make sense? Does that make sense, Rachel? Yeah, sweet.
Okay. Other than that, just watch some YouTube videos. Okay. last two things, you will go through this a million times as well. You need to know the characteristics of skeletal muscle, cardiac muscle, and smooth muscle. And this is very, very high yield for reasons I cannot explain. So skeletal muscle are cylindrical, they're striated, so they kind of have like lines going through them made up of actin and myosin, and you have multiple nuclei at the periphery of every cell. So every single thing that I have bolded could be a multiple choice question on your exam. And there have been multiple choice questions on this on exams before, so just remember it. Do I need to go through this? Let's just skip this one now, unless.
I think that was pretty high yield.
Oh, what's this high yield? Okay. All right. So when you have skeletal muscle, you have your axon, and this is what was covered last week or the week before. Your axon brings in like the action potential. Yep. So your action potential comes through, and then it releases some neurotransmitters. But the thing with skeletal muscle is that you want your contraction to be coordinated. You don't want some part of your muscle to contract and other parts of your muscle to not contract. So you want it to be a coordinated response. And in order to do that, you kind of have these things called T tubules. So your T tubules kind of run throughout, like they're like little highways throughout the cell, throughout the muscle cell, that the action potential can kind of like take shortcuts through. And surrounding it, you kind of have sarcoplasmic reticulum. So the main thing you kind of need to take away from this is, as the action potential comes down, it'll kind of propagate through like these T tubules. And then this will kind of trigger the sarcoplasmic reticulum to release calcium, I believe it was, to cause the different muscle fibers to shorten and essentially for your muscle to contract. Anything else to add to team? Anyone, Peter?
No.
Okay. Okay, skeletal muscle. You've got different types of skeletal muscle fibers. We didn't cover this in great detail, but it's very easy to memorize. So type 1 are your slow twitch fibers. So think back muscles, which need to, stay, contracted for long periods of time because you need to have good posture. And you also need to think of like long distance runners. So long distance runners can run for like 10, 20 kilometers, 50, 60 kilometers without dying. So those are your type 1 slow twitch fibers, and they're generally small. They have lots of mitochondria and lots of myoglobin, which is the thing that allows you to store oxygen. On the other hand, you have type 2 fast twitch fibers. So these are like your fast oxidative type 2A and fast glycolytic type 2B. So fast oxidative, they have lots of mitochondria, lots of glycogen, and they're very good at undergoing anaerobic glycolysis. So these are like your 400 meters and 800 meter runners. And then lastly, you have your fast glycolytic type 2B fibers. So these have less mitochondria, lots of glycogen, but they fatigue like really, really quickly. And for this, you just think sprinters. It's just a memorization thing. Good job on the multiple choice question. Okay, last two things. So you have your cardiac muscle. I don't know if you guys have gone through this yet, but you need to know their characteristics. So you need to know that they're striated and they're branched, and they have one or more central nuclei, and they're joined end to end by intercalated discs. So the reason why it's important that they're joined end to end at intercalated discs is because it's kind of similar to skeletal muscle in that you kind of want it to contract in a really coordinated way, and being joined into an intercalated disc allows like the action potential to like propagate directly through the muscle fibers. They have lots of mitochondria, and it's similar, sarcomeres. Okay, last one, smooth muscle. So these are like your muscle fibers in your stomach and your gastrointestinal tract. So they do not have striations. but they still use the whole actin-myosin interaction thing to like shorten and contract and relax and all that kind of stuff. They have a centrally located nucleus and actin binding dense plaques. I don't know what I highlight. I don't know why I bolded that. I've never had a multiple choice question on that. And make sure you are able to identify each type. So if you see that, you need to be like skeletal muscle, cardiac muscle, and smooth muscle. And yeah, there's a comparison slide here, and you can basically just memorize everything on here and you'll get everything. Okay, wonderful.
Okay, sweet.
Okay.
Thanks, Zoe. Okay, let's do. Do you want to do pharma next? Oh wait, there's a question. Okay, does slow twitch?
Pharmacology.
Yeah. I'll address the question. Does slow twitch generally have more actin and fast twitch have more myosin? Or is it the size of fibers unrelated to these ratios? Zoe, any ideas?
Slow twitch have more myosin.
Oh, I think I'm frozen.
I'm actually not too sure.
I have a feeling it would be. I have a feeling it would be the size of the fibers, because the reason why I think that is. Actually, no. I would rather not say this. No. That was just me trying to take a wild guess, and it's probably not correct. So I'm not sure what the reason is.
Yeah, main thing is you don't really need to know, or you can email his name, Mike. Yeah, I'm not too sure. Sorry.
All right. Gonna start on pharma.
Yeah.
Yeah.
Share screen. Okay, I think this week you will have a pharmacology introduction if you haven't already, and I'm pretty sure Richard took this one, so it should be a pretty good lecture. Okay, so first of all, starting off with a few definitions. So what is a drug? So typically the definition is any chemical substance other than a nutrient or essential dietary ingredient that brings about a change in biological function. And pharmacology is the study of the interaction of these drugs with the living system or with our body. And so here I've just included like a quick summary of like common endings that indicate like what drug class it is. However, you don't have to like go off and memorize these now. When you actually get to learning what these drugs do, it'll sort of come more naturally. So don't memorize these endings now if you have no idea what the actual drug is and what they do. So what are some sources of new drugs? One is natural products. 2 is serendipity, which is like a lucky accident or a happy chance. 3 is drug design, which is the main one. So most new drugs are synthetically produced from rational drug design. However, approximately 50% of drugs in clinical use are actually derived from natural products. And 4 is screening of chemical libraries. Not that important. So drug design is the main one. So this is the process of designing a drug to target a specific receptor in the body. So instead of starting off with a drug and trialing it to see what it does to the body and which receptors it'll bind to, which is more of a chance of luck, you actually start off by knowing exactly which receptor you want to target, identifying the shape of the receptor, and then designing a drug that will essentially be the correct shape to bind to that receptor. And so receptors are really important because they're the targets for your drug action, and essentially a drug will not work unless it can bind. So most drugs exert their effects by binding to protein molecules, such as your enzymes, ion channels, transporters, and other receptors. Okay, so different types of receptors. So they can be inside the cell, which is an intracellular receptor, or they can be on the surface of the cell, which is a cell surface receptor. So ligands, which is what binds to the receptor, such as your drug or your neurotransmitter, they'll bind to receptors via specific recognition sites. So essentially the ligand or your drug has to be the correct shape in order to bind. And so once it's bound, you'll get a biological response, which is initiated. So you could have an altering of protein function. So this is typically fast. So for example, your drug binds to a protein and inactivates it. So as soon as it binds, the protein can't work anymore, so that will be typically fast. You can also get a situation where the drug binds, however, it alters protein synthesis. This is typically a lot slower because you essentially have to bind to a cell, initiate a bunch of signals and pathways within the cell to actually either increase protein synthesis overall or to inhibit the synthesis of protein. So binding to receptors, Richard will talk about the induced fit model. So drugs bind and interact with the receptors through an induced fit model. So for those who've done bio, you'll have learned that drugs can either bind through a lock and key. So that's when the receptor and the drug are essentially a perfect match for each other. However, the main idea to get from this is that in reality, most drugs or almost no drugs bind via a lock and key model. Most of them will bind via an induced fit model. So what that means is the receptor and the drug aren't actually like a perfect 100% match. So when the receptor and the drug come in close proximity to each other, their chemical structures will essentially interact and you'll slightly change the shape of the receptor. So a conformational change occurs in the receptor and thus the drug can then bind and then there'll be a nice fit. Now, drug binding can be reversible or irreversible. So when it's reversible, you'll get ionic, hydrogen or dispersion interactions between the drug and the receptor. And so so everything other than covalent, essentially. However, you can also have irreversible binding, and one of them is aspirin. It irreversibly binds to this enzyme called COX, which you'll learn about later. And normally in irreversible binding, it'll either bind via covalent bonds or it'll bind so tightly that there's almost a 0% chance of the two dissociating. Yep, so this diagram over here essentially just sums up the whole pathway. So this gray thing here, let's say that's your drug. Chemical structures will interact with each other and it'll bind via an induced fit. So over here, it's now bound by an induced fit and a conformational change has occurred. Now, there are two ways. You can either have an altered protein function, which is fast, as we said before, or it can take a slower pathway, and that is it'll initiate a cascade of events that will influence DNA and RNA, so your translation, transcription on that level, and then that'll either activate or inhibit protein synthesis, so you'll have an altered protein synthesis, and then this will ultimately alter the cell behavior. So both of them have the same ending, but one is fast and one is slow, depending on which pathway you decide to take. So specificity versus selectivity. So specificity refers to, so if a drug is specific, it'll act on a receptor where the receptor can only be found on a specific organ. So for example, a drug that is highly specific to the heart will only target beta receptors on the heart. So it doesn't care if you've got beta receptors on the rest of your body. If it's very specific, it'll only target beta receptors on the heart. Selectivity, on the other hand, is essentially where the drug will act wherever the receptor exists. So if a drug is selective, instead of specific, it'll, let's say, target all beta receptors within the body. So if it sees one on your heart, it'll go there. If it sees one on your skeletal muscle, it'll bind there. If it sees one on your lungs, it'll also bind there. So it doesn't care what organ it is. As soon as it sees a receptor that it can bind to, it will bind there. So the sad part is drugs are usually selective rather than specific. So even if you just wanted to target the heart, most drugs aren't able to do that. So most drugs will just at the same time target other parts of your body, and that is one of the main causes for a lot of adverse effects. And most drugs are relatively selective. There's also this thing called affinity versus efficacy. So affinity is essentially the strength of the binding of a drug for a receptor. So this could be low or high. And so Ka is the measure of the affinity. That's not too important. So if it's got a low level of affinity, it means that the drug doesn't bind very tightly to the receptor. Whereas if it's got a high affinity, then the drug binds very strongly to the receptor. Efficacy is the capacity for a drug receptor complex to actually generate a response. And this is denoted by this symbol here. And essentially, we want drugs with both a high affinity, so you know that it will bind, and once the drug binds, it will bind very tightly. And also high efficacy, well, because even if the drug binds, if it doesn't elicit the response we want, there's really no use in giving the drug. So that's why we want both high affinity and high efficacy. We also got what's an agonist and an antagonist. So you can think of them as agonists as activators and antagonists as inhibitors. So agonists are able to bind to the receptor and essentially activate it. So it'll have affinity because it's able to bind. Agonists also have efficacy because it's able to activate the receptor and initiate change. Antagonists, they're able to bind. So yes, they do have affinity because they have to bind to the receptor to do something. However, they cannot activate it. So they kind of block it instead. So therefore, we say that antagonists have zero efficacy because they're actually not able to initiate any changes in the cell. It kind of just blocks other substances or other molecules from activating that particular cell. Yeah, and I think that's it.
That's sweet. Does anyone have any questions about that stuff, about pharma? Pharma will kind of come up quite a lot. So if you feel like agonists and antagonists aren't making sense, they'll come up later on and like they'll just keep bombarding you with all those terms. So it'll become clearer over time. Who did
it's
cancer?
Like in year 12 bio, most people said activators.
Yeah. I'll share my screen.
Okay.
Yeah.
Okay, so for cancer, the main definition that you need to know is that it's just the abnormal and uncontrolled division of cells. So this is very important because before you even came to medical school, like you probably assume, and many people who are unaware of like the actual definition of cancer, they'll just assume that all cancer is bad and it's always going to harm your body. And that's not necessarily true because you can have an uncontrolled division of cells and that could just be benign and may not result in a malignancy. Okay, so normal cells, they become cancer cells because there's an accumulation of genetic errors. And this whole process of it transforming into a cancer cell is called transformation. And they can arise from anywhere in the body and they form solid masses of cancer cells termed as tumors. Okay, so you probably have a few histology sessions on these, but the main features of cancer cells that you need to know is that they are resistant to inhibitory growth signals, and I'll go through that later. And they have accumulated genetic errors. They have an active telomerase. So this is something like you should know about because telomerase is an enzyme which replenishes telomeres. So if you recall, telomeres, they cap chromosomes and they indicate the age of the cell, and they basically shorten upon division. So every cell has a specific age. but certain cells which lack certain cells whose chromosomes have very short telomeres, they just basically undergo apoptosis. And cancer cells, they can avoid undergoing apoptosis, so they're essentially immortal. And they also can escape immune surveillance. So you're studying in microbiology how you have got your PAMs and your DAMs. These cancer cells, they mimic the self molecules of body cells, so they escape the whole immune system. There are a few features of cancer cells that you need to know on top of that. So these are the main ones. And on top of that, you need to know that it has an enlarged nucleus. It's immature, it basically doesn't develop properly, so it loses its specialization. The two main things about inhibitory growth is that it has no contact inhibition. So normal cells, when they come into contact with other cells, they stop growing. So like cells don't form layers upon layers, normal cells, whereas cancer cells will form layers upon layers, and that's how you form a tumor. And it doesn't have a anchorage dependence. So cancer cells do not need to adhere to a layer of cells. They can just detach and still survive. That's how you have cancer spreading to other parts of your body. It also has reduced requirement for external growth factors because cancer cells can produce their own growth factors, whereas for normal cells, they require these external growth factors for them to even grow bigger in the first place. And another thing is change in cytoskeleton. Okay, so development of cancer, it can be inherited, but it's the minority of cases, and it can be somatic, where cancers can mutate due to mutations such as smoking, radiation, viruses. So the main thing that you need to take away is that in order for a cancerous cell to develop, it requires at least 4 to 6 mutations in the cell, and these mutations can occur in 3 types of genes. So you need to know these 3 main ones: oncogenes, tumor suppressor genes, as well as mismatch repair genes. So oncogenes, before we go on to oncogenes, you just need to know proto-oncogenes are good for you. They promote healthy cell growth and division. And mutations to these proto-oncogenes result in oncogenes. And oncogenes cause inappropriate cell division. It basically causes increased cell division, and that promotes cancer. It's a one-hit hypothesis. So all these 3 different genes have a different set of hypotheses, so you need to know that. So for oncogenes, it's one-hit hypothesis, which means if you have a mutation in just one allele, it's sufficient to cause cancer. And it's a gain in function mutation, because if you notice, your initial proto-oncogene promotes healthy cell growth, and it stops it to a certain point. Like your cell can't grow any further. Whereas once it's mutated to oncogene, it's gain in function because your cell can continuously grow. Okay, so tumor suppressor gene. Tumor suppressor genes, you need to know your P53 and retinoblastoma. These are very important. They control DNA repair proteins, and they control your cell cycle checkpoint. So if you remember your S phase, G1, G2, and it's a 2-hit hypothesis, so it requires at least 2 mutated alleles to cause cancer. And it's a loss of function because initially you have these tumor suppressor genes which control your cell cycle, and when they are mutated, they no longer control the checkpoints, and so your cell can just continuously replicate. Okay, so your P53 is a protein which is involved in arresting the cell cycle, and the tumor suppressor gene is responsible for inhibiting cell growth. So when it's mutated, it becomes non-functional, and the cell loses ability to halt at the G1 S checkpoint. So the cell usually needs to halt at different checkpoints in order for the cell to go through like a vigorous check to see if there's any mutations. And without this P53, there's no such process, and so there's no time to repair the DNA, and this just causes an increased risk of mutations. And so this is the most common gene for 50% of cancers. Okay, mismatch repair genes is the final one. So mismatch repair genes, they repair mutated DNA, and they repair DNA during your S phase. So again, this is also a two-hit hypothesis. So it requires two mutated alleles to cause cancer. And again, it's a loss of function mutation because again, once this gene is mutated, there's no repair of DNA. Okay, metastasis is the invasion of and spread of cancer cells from your primary tumor to a secondary area. So you have different stages of metastasis. So how metastasis actually works is that cancer cells secrete enzymes which break through the capillary. So your cancer cell is initially located just above your basal membrane, and below that is the capillaries. So your cancer cells secrete enzymes which break through the capillaries, then they flow through the bloodstream, and they adhere to the different capillaries and exit into different tissues. So once they exit to different tissues, cancer cells can then secrete this substance known as VEGF, which is vascular endothelial growth factor, and they promote angiogenesis. And this is basically the growth of new capillaries. So when there's increased blood supply to these cancer cells, allows them to actually get more nutrients and allows them to remove waste products and allows them to basically survive and grow further. So these tumors can just remain dormant and actually survive on for many years before this is successful, or they could just rapidly multiply. So like I was saying, there's different types of tumors. So not all tumors can cause harm. So benign tumors, they do not spread. So because they're actually held in place due to the fibrous capsule surrounding cells, and they resemble normal tissues. So they do not usually cause problems unless they are growing in confined spaces like your brain. But malignant tumors have a high rate of metastasis and invasion of surrounding tissue. So they do not resemble original tissue, and they are the main, they are basically problematic. So if you notice in this diagram, your malignant ones are really quite different from your benign or normal tissue, normal types of tumors. You can notice like the real loss in shape, and this is just a progression of how from normal it just gets worse all the way to malignant. And you'll be going through this in your histology. Okay, so effects of tumors. So they displace normal tissue and they deteriorate tissue function. So when that majority of the tissue becomes a tumor, it's unable to perform specialized functions. And if it spreads, it can block lumen of vessels like your capillaries, your arteries. And these tumors require a lot of energy in order to grow. And so this high metabolic requirements stimulates breakdown of other cells, and that causes a patient to actually lose weight. And this term is actually known as cachexia. Okay, so cancers can be inherited, even though it's a small minority. But indications that cancer is inherited, you need to take note of quite a few of them. So penetrance. So different cancers have different penetrance. So it's actually the percentage of individuals with the affected gene who develop the cancer. So certain cancers have a high penetrance, whereas certain cancers, even if you have a familial background of having the cancer, may not necessarily get that cancer. Okay. So you can have, if you have several relatives with a common cancer, that also increases the risk. Or if you have relatives with the same rare cancer, that also increases risk. Early age, bilateral cancer. So if you have cancers on both breasts, ovaries, or eyes, that's actually a sign of inheritance. Or if you have tumor in two different organs. Okay, so these are a few examples of inherited cancers. So colon cancer is actually caused by FAP, and FAP is caused by mutation in the APC, which is a tumor suppressor gene. So this is actually this cell is actually responsible for cell adhesion, and it's almost 100% penetrant. So that means that if you have a familial background of relatives having the cancer, it's 100% likely that it'll be passed on. So these polyps begin as benign, but eventually become malignant, so they must be removed. And if spotted early, they can be removed without any further complications. And again, so if it's a colon cancer, it can cause malabsorption of nutrients. So breast cancer, you'll see these terms commonly. You don't need to memorize or anything, but BRCA mutation happens at 17q. BRCA2 mutation occurs at 13q. It's just something they'll see quite frequently. And individuals with breast cancer are predisposed to ovarian cancer. And it also has a pretty high penetrance rate from 40 to 70. And indications that it's actually inherited rather than spread through somatically is that if it's bilateral and if it's concurrent with ovarian cancer and if it's early age. And one main thing is that if it's a male breast cancer, it's highly likely that it's inherited as well. Retinoblastoma. So I was saying this earlier, retinoblastoma is one of your tumor suppressor genes. And if there's a mutation in retinoblastoma, it affects your eyes. So in hereditary, it occurs at a young age and it occurs in both eyes. And it's a mutation in every cell. If it's sporadic, it occurs much later in your life, and it only occurs in one eye, and mutations in some cells. So it's mainly the somatic cells. Okay, this is another thing that you need to know. It's chronic myeloid leukemia, so CML. So this is you should have learned translocation by now. So when one gene is fused with another gene, it causes a shortened chromosome. And this shortened chromosome results in increased production of this protein. Okay, and this protein just causes your tyrosine kinase receptors to be permanently activated. You don't need to know these in detail, but it just helps you to better understand this whole disease. So these tyrosine kinase receptors are responsible for cross-phosphorylate. Basically, they allow for ATP to phosphorylate, and it just results in uncontrolled production of myeloid cells. So myeloid cells will include your macrophages, your dendrites, and they do not specialize, so they become immature, and this results in a weakened immune system. Okay, nice.
Okay, cool. So I think if you haven't, does anyone have any questions about the cancer stuff?
I think there's a question in the chat. Yeah.
Oh, yeah.
The mutation is the thing that's responsible.
Pretty sure FAP is due to a mutation in the APC gene, and APC is a tumor suppressor. So if you have a change in the tumor suppressor, that means that tumors can no longer be suppressed, and you get like literally hundreds, if not thousands, of these polyps or like early stage cancers growing all throughout your colon.
Yeah, FAP is just a term for the polyps that grow.
Yeah, FAP is just one genetic condition that can lead to colon cancer. You can also have sporadic colon cancer, which is where you just develop colon cancer without actually having any commonly known genetic underlying conditions such as FAP. The reason why FAP is mentioned is because of its near 100% penetration rate. So pretty much by a very, very, very young age, 100% of anyone who has FAP will have developed colon cancer. Yeah.
What is responsible for the cell adhesion then? Is it APC?
Yeah, so
Yeah.
your APC is this particular gene which helps to stimulate cell adhesion as well as signal transduction. But if there's a mutation to that, it just causes benign growth.
Yeah, because so APC is responsible for those actions, cell adhesion. So that's talking about the adhesions of the epithelium or the surface cells to the basement membrane. So therefore, if there's a mutation there, those cells can kind of detach and they can move around, that kind of thing. Yeah. Does that kind of answer your question about what APC does? I'll probably say it's not too important. Like it came up once, like last week for us, but the main important thing to remember for FAP is just that due to the number of polyps or the number of abnormal growths, like hundreds if not thousands, at least one of them are bound to grow into a cancer. Okay. Okay, so next we'll be moving on to blood stuff. So we'll have, yeah, okay, cool. So essentially you'll be talking about blood. I'll be talking a bit about clotting. But yeah, so first we'll talk about the composition of blood essentially, and it's made of a couple of layers, and we can use kind of two models to differentiate these layers. So when we separate it, it forms three layers. So plasma, which is kind of like the water of it, and then we have white blood cells and red blood cells. Erythrocytes are another word for red blood cells, and we also shorten down white blood cells into WBC and red blood cells into RBC, which I'll be using quite a bit in the future slides, just because it'll make our life a bit easier. Now, if we think about what our plasma actually contains, it's going to be containing just a bunch of water, metabolites, which are just outputs of our metabolism processes, has a bunch of nutrients and proteins. And then we have formed elements, which are all of our different types of cells. So our red blood cells, white blood cells, and platelets. Platelets are important for clotting, and we'll be talking about that soon. So how do we produce this blood? Well, we produce it through a process called hematopoiesis. And an important fact to know is that you need iron, vitamin B12, and folic acid to produce your blood. The reason this is important is because if you're lacking any of these three inputs, that could result in you being anemic. And that's important not only for year one, but also year two and onwards. She'll talk about, the lecturer will talk about different locations for blood production. And the main thing to take away here is that before you're born, so as a fetus, it's forming outside the blood cavity, so outside of your bone marrow. And then once you're born, it will start being formed within your bones. So extramedullary turns into medullary, and that's the main fact to know. We can see kind of how they're produced here, and it's essentially a process of differentiation from these stem cells into either myeloid or lymphoid, and then from there they split off into more specific types. This is quite a, there are a lot of different names here, and it could be a bit difficult to remember. However, if you're keen, I think it would be worth memorizing this, or at least memorizing which types of cells are from myeloid origin and which types of cells are from lymphoid origin. You can kind of remember it a bit similarly. So all your myoblasts have the ending phils, eosinophils, neutrophils, basophils, and then erythrocytes come from pro-erythrocytes, so beforehand. And an important type is a megakaryoblast, which has multiple nucleuses, will turn into your thrombocytes or your platelets. Yeah, so I would try to memorize this, but it's not 100% necessary. So erythrocytes, kind of be talking about the structure and how they work. So they're biconcave discs. So they You've probably seen the images of them. They're just circular discs with little indentations on each side. And this shape helps to absorb oxygen and transport it around. And this shape is essentially maintained by ATP as well. However, these cells do lack a nucleus and lack organelles, so they're very basic types of cells. Their pure function is to carry oxygen towards the tissue and remove toxins or metabolites from those tissues and expel them through the lungs. And once they've kind of reached their lifespan, they're removed through a certain system within the spleen and within the liver. But you don't need to know too much about that. Just know that they kind of have a really short lifespan of 120 days, and they're eventually removed and recycled. So in order to regulate this whole process of making red blood cells, we have a few enzymes. No, I didn't include an image. So essentially what's going to happen is we'll look at this third dot point. So if your blood oxygen saturation, or the amount of oxygen in your blood, is too low, this is sensed by your liver and your kidneys. And as a result, you're going to release a hormone called erythropoietin. And this will stimulate red bone marrow, so within your bones, to make more red blood cells. And as a result of having more red blood cells, you're going to be able to transport more oxygen. And by transporting more oxygen, you're going to be increasing your oxygen saturation. So therefore, it's kind of like a negative feedback loop, if anyone has done 1-2 bio. So we start off with low oxygen saturation, we make more red blood cells, and that increases our oxygen saturation. So that's our hematopoiesis, or our red blood cell formation. And then we also have leukopoiesis, or white blood cell production. And this one is regulated through colony stimulating factors, or CSF, interleukins, which is a type of cytokine, as well as immunological stimuli. So this stuff here, since it's a white blood cell, it's going to be due to infection. And if it's due to infection, I guess the main thing to remember here is that your immunological stimuli, or your different pathogens, are going to be stimulating its production. Okay, so if we jump back now to red blood cells and we think about their metabolism. So one of the functions of red blood cells is oxygen uptake, and to do that, it has to maintain this biconcave shape, or this disc shape. And within our red blood cells, in order to carry our oxygen, we have something called hemoglobin. And hemoglobin is a polypeptide, a quaternary structure, and it has 4 globin chains. So 4 different polypeptides, 2 alpha and 2 beta. And essentially all of these globin chains will have an ion group, or something we call a heme group, and this will allow it to uptake oxygen. So each red blood cell will have a couple 100 million of these hemoglobin, and each hemoglobin will have 4 globin chains, each with a heme group. The important thing to take note from here is that the order that we fill up each hemoglobin. So if we imagine these hemoglobins as cars, each car can take 4 passengers. And the way it makes most sense to fill up these cars is to fill up one car fully before moving on to another car, because it doesn't make sense to put like 2 passengers in one car and then 2 passengers in another car when you could just put 4 passengers in a singular car, if that makes sense. So each hemoglobin will always fill up with 4 oxygen molecules before other hemoglobins are filled. And ATP is provided through glycolysis and the hexose monophosphate pathway. And the reason that it's through glycolysis is because they lack organelles. They don't have mitochondria, so therefore they produce their small ATP need through glycolysis, or an anaerobic pathway. Now this is a small graph that you'll touch on for a short amount of time during year 1, but it'll mostly come up at the start of year 2. And what this graph shows is it shows the partial pressure of oxygen. If you remember partial pressures from Chem 3-4, but it's essentially the pressure of oxygen in the air that you breathe. And on the y-axis, we have the percent saturation. So how much of our blood will fill up with oxygen. And as we can see here, in order to get like high 90% saturation, we're going to only need about, we're only going to need like 70 odd, 60 odd millimeters of mercury in order to fill up our red blood cells. And the main thing to note here is what happens to this shift. So if we have a right shift, or if we move this curve over to the right, that means that you're going to need more oxygen pressure in order to fill up our red blood cells. And this right shift can be caused by increasing the temperature, increasing a molecule called 2,3-DPG, or decreasing the pH, or increasing the hydrogen ions. So you can think of a right shift as reduced affinity. So our red blood cells don't really want to join onto our oxygen. So therefore you're going to need more pressure from the oxygen in order to jump on. And then the opposite of all that is something called a left shift, or a reduced, or an increased, affinity. So all the opposite things. So decreased temperature, decreased 2,3-DPG, increased pH, or decreased hydrogen ions, as well as carbon monoxide. If you don't understand this one, don't worry too much. It'll come up again, so they'll try to continuously drill it into your head. This stuff here is what I was talking about when I was talking about the short lifespan of red blood cells, so about 120 days. And since all of our red blood cells have iron, it's important to recycle this iron, so that we can use it to build other cells. And it'll come in this flowchart here. And this flowchart you will need to memorize. This flowchart is super important, not just for year 1, but also for year 2. And like we've literally just done this again. So our hemoglobin can be split into the heme, or the iron unit, as well as our globin chains. Our globin chains, since they're proteins, will go to our plasma proteins, and they'll get broken down back into amino acids in order to produce other proteins. And then if we think about our heme will get broken down into our iron. And our iron will be combined with biliverdin, as well as carbon monoxide. And as a result of this, our iron will get combined with transferrin, and this will go back to our bone marrow. And in our bone marrow, our iron can be recycled in order to produce more hemoglobin. And as a result of our biliverdin and carbon monoxide, this will get converted to bilirubin. And within the liver, this will get conjugated, or something will be added onto it, and it will turn into urobilinogen. And if it's a urobilinogen, this will allow it to be excreted through either our feces, by flowing through the duodenum, small intestine, and the large intestine, or it can be excreted through the blood and filtered by your kidneys before you pee it out. It can also turn back into bilirubin, but it'll come back again into urobilinogen to be eventually excreted. Once again, this flowchart will come up again during year 2 when you look at the GIT. So it's fairly important to know. Thrombocytes are platelets. These are important for clotting. And the production of thrombocytes is the regulation of thrombocyte production is through thrombopoietin. So if you see any word with poietin at the end, that's going to be a hormone or a type of chemical signal that will control the production of the certain type of blood cell. There are a ton of abnormalities. Your lecturer will go through a lot of them, but the main ones are to do with number. There are also other abnormalities to do with like their metabolism and their shape and some of their functions, but I found those ones aren't as useful and numbers most useful. So for hemoglobin, our red blood cells essentially, anemia will be low levels, and polycythemia, poly meaning many, will mean higher hemoglobin. Similar for leukocytes, low levels will be leukopenia and high levels will be leukocytosis. Platelets, low levels will be thrombocytopenia, high levels will be thrombocythemia or thrombocytosis. The other important thing for platelets is that you can have adhesion disorders, and this will be when your platelets join up too easily or they don't join up at all. And this can result in you forming blood clots too easily, which could lead to like a stroke or you losing blood supply to a certain part of the body, or it could result in you bleeding out and not being able to stop the bleeding. Do we want to finish off with clinical skills then?
I can go through vital signs, or we can go through it next time. Up to you guys.
Does anyone have any questions?
Yeah. We could probably go through it next time if, like, when more people are here, because it is. Oh, till sem 2. That makes sense because you can't like do it online. Yeah, I can go through it next time, just as like a a fun fact.
Yeah, let's go through vitals next time then.
Yeah.
And figured. Yeah, us too, I think.
Try to show Buddy. Oh my god, guys, Buddy is
He your last lesson.
Yeah.
Wait till your last lesson with Buddy. He'll sing you a song.
He sings you a song about for Sem 1. He sung us a song about WWQQ AABA. Like he literally sung us a song. He wrote it and like he sung us a song about how to take a history, and it was literally the best thing, the best moment of my life.
I had Buddy for the whole year, and I got 2 songs from him.
Oh, did you?
Yeah.
Oh, so lucky.
He's such a blessing.
Except I had Robin.